This conference will now be recorded.
Good afternoon, everyone. Whether it's audible?
Hi, good afternoon. Yes, it is audible.
Yeah, audible.
Yes. Today here we are to proceed with the synthesis and STA demo. Today we have to start with the synthesis and STA demo. We'll wait for 2 minutes, then we'll continue. Okay. Yes, good afternoon, everyone. Here we are to start with the synthesis and STA demo session. Right? So when we, so mainly, right, the synthesis is done, right? Synthesis is a ASIC design flow step. In ASIC design flow, synthesis is a step. Right? So when we start with ASIC design flow, when we are designing any design, right? When you start with ASIC design flow, so first we start with specification. Right? We start with specification. Next we start with RTL coding. RTL coding. In RTL coding, we generally use Verilog or VHDL, right, to describe the design. To describe the design, generally we use Verilog or VHDL to describe the design. So, can I ask why Verilog or VHDL is used to describe any design? Right? Why we have to describe any design through Verilog or VHDL? Yes, can anyone tell me why we have to describe a design by using Verilog or VHDL or any programming language should be used to describe a circuit by using Verilog or VHDL? Why it is required? Because Verilog or VHDL can be easily used, right, to describe a circuit by its behavior way. Verilog, or I can write HDL, right? HDL means hardware description language. HDL can be, HDL means Verilog or VHDL. HDL can be used to describe any circuit, right, in its behavior form. That is easy to describe any circuit by its behavioral form. So design entry doing through RTL coding is very easy. Right? So for example, I take one example, right? If I ask a mux, if I ask a mux, so if I ask the internal structure of a mux, I ask you people to give me the internal structure of a mux. So explaining internal structure of a mux is very difficult. You cannot explain that. You cannot explain the internal structure of a mux. You can explain, only few can explain. But if I ask the behavior of a mux, right? If I ask a behavior of a mux, I have I naught, I have I1, I have Y, I have signal, right? I have a select line. So, but if I ask explain the behavior of a mux, everyone can easily explain, right? Everyone can easily do that. So you have select line, you have output pin Y. If select line is 0, output pin Y is going to take I naught. It's going to take I naught. If select line is 1, right, output is going to take I1. So everyone can easily explain this. This circuit. This is the behavior of a circuit. So through HDL, behavior can be captured easily. Right? So even HDL has if statements, case statements, procedural statements, blocking, non-blocking statements. Right? So if you can directly use this, right? If S equals one tick binary 0, right? If that is the case, then what you do is Y is assigned with I naught, else. Else means if S is not equal to 1, else then Y is assigned with I1. I can easily describe the behavior of a mux. I'm just giving an example. So describing any circuit through its behavior is very easy. Instead of going into the internal structure, I have a ALU, arithmetic logic unit. I have two inputs, two 8-bit inputs like A, B, right? And I have opcode like OP. I want to perform like for basic things. I'll take like this ALU is going to perform addition, multiplication, subtraction, division. If this opcode is 0, 0, right? What y will take? Y is going to take A plus B, right? If y is 0, 1, sorry, if opcode is 0, 1, this opcode is 0, 1, y is going to take A minus B. If opcode is 1, 0, y is going to perform A multiplied by B. If y is 1, 1, y is 1, 1, A is going to perform A divided by B, division. So just explain the behavior of a ALU by its behavior, right? Explain its, do the design or describe the design by its behavior. That is easy using RTL coding. We can use similar to C programming. You can use if statement. We can use case statement and describe the behavior. Right? This is very easy by using RTL coding. For that reason, we use hardware description language with variety of operators and packages. Right? We define any circuit by its behavior. Like for example, if you have a bigger circuit, we define it through FSM, finite state machines. In this state, my circuit will behave like this. In another state, my circuit will behave like this. So for that reason, we use RTL coding. So, but the chip, right? The chip what we fabricate, the chip is fabricated. Chip is fabricated. Chip, right? Whatever we are fabricating chip, the chip is fabricated in foundry. The foundry can understand only layout information. This foundry can understand only layout information. Layout of a standard cells it can understand. So this information my foundry can understand. RTL coding my foundry can understand. Foundry is a place where chip is fabricated. So some chemical process they work in nanoscale, right? This behavioral structure my foundry can understand. So then next step of this ASIC design flow is third is functional verification. As you people already know, right? The functional verification. Next step of this ASIC design flow is functional verification. See, functional verification, what I do, if I take this mux example, same mux example, right? If I take the same mux example, I'm going to apply different test cases for inputs and I'm going to output verify what is the output. For I naught, I'm going to apply different input. For I1, I'm going to apply different input and yes, I'm going to apply different inputs like 0, 0, 0. I naught is going to take 0, I1 is going to take 0, S is going to take 0. And what is the output? Verify. Next, apply different test cases 0, 0, 1. I naught 0, I1 0, S is 1. 0, 1, 0. 0, 1, 1. Like this, right? Till end 1, 1, 1. Apply different test cases and verify the design. So this is called as a functional verification. After RTL coding, right, any block or any chip, right, after RTL coding, that will enter into functional verification stage. So during functional verification, we verify we verify functionality of a design. The functionality of a design is verified by applying different test cases. By applying different test cases. Test cases means different inputs. Apply different test cases and do functional verification. But this can be done very easily if I have less number of inputs. Like if my bus is having only 3 inputs, right? I0, I1, I2, the number of combinations are 8. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. I have 8 combinations. But, right, if I have a bigger circuit with like 200 inputs, then doing function verification is very easy, very difficult. I cannot use all the test cases to function verification. To do function verification, I cannot use all the test cases because I have 200 and 2 raised to power of 200 combinations. I cannot do all the, I cannot apply all the test cases. So we have, all right, UVM, and we have to learn system verilog here. System verilog to verify the design with minimum test cases. Minimum test cases. That is what we do in functional verification. In functional verification, just the RTL code, whatever we have, we are going to verify. That's it. Whether it's working properly or not. But this behavioral description of a RTL code cannot be understood by Foundry. Foundry can understand the layout information. So for that reason, what I do is next is behavioral information. I convert into gate level information, gate level connections. Right? That is what called as synthesis. Right? So next step, right, of this, next step of this process is synthesis. Convert gate level design, sorry, convert RTL into gate level design. It's called a synthesis or gate level netlist. Directly, I can use the term gate level netlist. That is called a synthesis. So our area of interest is this one only, right? Synthesis only is our area of interest. So after synthesis, what we do is we do PD, physical design. In physical design, convert gate level design to physical design, right? Physical information means layout. Each and every cell what I have in the net synthesis netlist, right? For each and every cell replaced by the layout and make the connection through metal layers. That information, if converted to GDS file, that I forward to Foundry. So gate level design, right, to physical information. This logical information convert to physical information, like you use right chip, create a chip like this, and here you place all the standard cell by its layout inside the core area. This is called as core area. This is called as die area. You have core area, you have die area. So inside this core area, we will place all the layout of the standard cells and macros, and we connect them through metal layers, After this, we will create a GDS file. It's having complete layout information. Then that will forward to Foundry. So Foundry can understand only this layout information. So synthesis is going to act as a step between this, right? So even you have many steps in between, like DFT you have. I'm just explaining in brief. Synthesis is going to act as a step between this. It is going to convert your behavioral description into gate level netlist. This gate level netlist is taken by physical design team and they are converted into physical information. So bridge between these two things, physical design and RTL team, is synthesis. Now we will discuss about only synthesis. What is synthesis? Already we have discussed what is synthesis, right? Synthesis is nothing but converting RTL into gate level netlist. First, I'll discuss about logic synthesis. Logical synthesis. Convert RTL into gate level netlist. Can anyone tell me what are all the inputs for logical synthesis? Inputs for logic synthesis, to perform logic synthesis, what are all the inputs? Can anyone tell me?
Verilog netlist.
Yes, it's a very like RTL code, right? This
Yes.
RTL code. This RTL code is required. So RTL code, one of the input is RTL code. This RTL code is present in a behavioral form that you have to convert into gate level. So next, what is another input?
UPF.
UPF, that will come later. Basic inputs. What are the basic inputs required?
SDC.
Yes, STC is required. Correct. And before STC, we want see. I am telling that RTL to be converted into gate level netlist. So who will give this gate level information? This RTL should be converted into what gates? What gates I have to convert at last? Right. Which gates I have to use for this conversion? So this gate level information is present in library file. Library or liberty file. Liberty file, that is dot libs. I want dot libs. So in dot libs, what we have? So we have standard cells, right? What do you mean by standard cells? AND gate, NOR gate, NAND gate, AND gate, XOR gate, full adder, half adder, mux, D flip flop, AOI gate, OAI gate. All these are called standard gates, standard cells. They are called standard cells because almost they have same height. In physical design, they are placed on the side rows. They almost have same height. So for all the standard cells, right, in the Liberty file, for all standard cells, we have timing and power information. So timing means like what is the output transition. We have table. For delay table, we have max capacitance value, max transition value, setup table, setup time table, hold time table. Right. All this information is called as timing information, power information. It has leakage power and internal power. So Liberty file and library file is very important. Whether this Liberty file or library file is a technology dependent or technology independent. Liberty or library file. Lib file. See, your lib file is a technology dependent, right? It is technology dependent. So you will get this file from library characterization team. There is a library characterization team. You will get from library characterization team. So library characterization team, they will get the spice models for particular technology. Like they will draw the inverter, right? This is the inverter. They will draw the inverter. They'll get all the spice models like PMOS and NMOS. You will get the spice models, input and output, right? Is a PMOS spice model you will get, NMOS spice model you will get for particular technology. Means for 28 nanometer you will get spice models for them. So with this spice models they'll do a simulation for different input transition, for different output loads, output load capacitance. They will find delay of the cell. They will find power consumption of the cell, and they will record in a file called as a Liberty file. So the library file or Liberty file is a technology dependent file. So next file, what is required? Can anyone tell me? Next file, what is required?
Techless.
TechLef is not required for logic synthesis. TechLef is called in cadence, and technology file is called in synopsis. So that is required for physical level synthesis. For logic synthesis, TechLef is not required.
SGC then.
Yes, sir. HDC is required. Very, very important HDC. So HDC stands for what? Synopsis,
Design constraints.
design constraints. So this synopsis design constraints file has timing constraints. It has timing constraints. So we have to write this timing constraints. So it is having timing constraints like different types of clocks. So in design, right, we will study that different types of clocks, master clock, generated clock, virtual clock. So we have different types of clocks. So max clock transition or clock transition, clock uncertainty, clock uncertainty, set driving cell, driving cell, load on the output ports. What is the load on the output ports? Set input delay, set set output delay. And PVT corners for particular PVT corners. So all this information, right, basic information like all this information is present in synapse design content. So different types of clocks and their frequencies or periods and their clock periods. Right? This is called as a synopsis design content file. So we will study that how to write. I have to write all these things in for the design. Right? How to write all these things. We will study about that. What is the meaning of each and everything, and how to write all these things. Right? We are going to study about this. See, I have to do the conversion like RTL to gate level netlist. Right? I want to do the conversion by following these timing constraints. I want to meet this clock period, whatever the clock period is there. I want to meet that, meet this. I want to meet this clock period. Without meeting this clock period, I cannot perform it. Synthesis cannot be performed. We should not do the synthesis. I want to do the synthesis in such a way that I want to meet this clock frequency. Right? So for that reason, it's called as timing constraints. So by taking this information, so even few informations are required like UPF. It is a multi for low power technology. Right? If you are using low power technology or low power technology or low power technology, like we have multi voltage design. If we have multi voltage design, or if we have power getting design, if we have power getting design, we need UPF also. So UPF stands for Unified Power Format. You want to, we also UPF stands for what? Unified Power Format. Even this UPF is required. So we will also understand how to write this UPF for multi voltage design. We'll also in this course we'll also write SDC, and we'll also write UPF for multi voltage design. We'll understand how to write UPF. So these are all the inputs required for synthesis. For logical synthesis, these are all the inputs required. So by taking all this information, my tool will convert RTL into gate level netlist. So what do you mean by gate level netlist? Right? So what is output of synthesis? Output of synthesis, logical synthesis. I'm talking about logical synthesis, right? What is output of logical synthesis? The output of logical synthesis is gate level netlist. So in gate level netlist, what is gate level netlist is also a Verilog program. RTL is also Verilog program. Verilog or VHDL, right? RTL is Verilog or VHDL. Even this gate level netlist is also Verilog or VHDL. Even this is also Verilog or VHDL. Then what is the difference between RTL and gate level netlist? Can anyone tell me?
Technology dependent.
Yes, very good. Right. RTL is in the behavioral form. Gate level netlist has gates and its connection. That's it, right? It should not have any other thing. It has only gate and its connection. You should not be having any other things. In gate level netlist, you should be having only gate and its connections. But RTL has the behavioral form, right? It can have if statement, it can have always block, it can have case statement, it can have assign statements. But in the gate level netlist, you should be having only inputs, outputs, wires declared, and you should be having gates and its connections. That's it. So everyone know what is how does the netlist resembles, right? Everyone knows that. For example, you have for example, I have like this, right? I have like AND gate, like OR gate, and I have like inverter, like little bit big also. I have AND gate, I have OR gate, I have one inverter. Like this is our gate level netlist. This is a gate level diagram. So this inverter is connecting like this. This AND gate is having A1 pin, right? A2 pin, Y pin. Alright. This OR gate is having A1 pin, A2 pin, right? Y pin. This inverter is having A pin and output as Y pin. So in between you have nets, N1 net, N2 net, N3 net. Net is nothing but object which is connecting from one gate to another gate. You have N4 net, N5 net, and N6 net. So this AND gate, the name of AND gate in library is AND2, means like two input AND gate. This OR gate, the OR gate is OR2, inverter, right? The name is inverter. Then how do you have this, right? How do you have this netlist? Can anyone tell me what is a netlist? How do you have this netlist? So netlist has same thing, right? You have module name, like module name I use it as design. Like you have inputs and outputs declared here. Next you will declare what is the inputs and your
Input
output
wire, output
declared.
wire.
And here you have wire declared, wires, how many wires you are using. And you have just mapping of the ports, right? First you are having AND gate and two input AND gate. You're having two input AND gate. So along with this AND gate, synthesis tool will give one instance name. That the instance name for AND gate is U1, instance name for OR gate is U2, instance name for inverter is U3. So instance name is given because I can have plenty of AND gates in the design. So I should be having some difference, right? One AND gate to another AND gate. For that reason, synthesis tool will give this instance name. So first use this library name and two input AND gate. Instance name is U1. Instance name is U1. Then do port mapping. Open bracket dot A1. For A1 pin, what is connected? N1 net is connected. Right? N1, comma. Dot A2. What is connected? N2 net is connected. Dot A2 pin, N2 net is connected. So Y pin, right? You have Y pin, dot Y. For Y pin, what net is connected? N4 net is connected. I don't have space here. I'm writing here. Over. Next is OR gate, right? You have OR gate, 2 input, right? Instance name is U2. Then you do port mapping, right? Dot A1. For A1, which net is connecting? N4 is connecting. Dot A2, comma, dot A2. For A2, which net is connecting? N3 is connecting, comma. For output pin, right? Output, which net is connecting? F5 is connecting. Output pin of OR gate is connecting to N5 net. Next, I have inverter, right? This inverter with U3 instance name. So you have input pin dot A is connecting to N5 net, comma. We have output pin Y connecting to N6 net. And end module. Just I am giving the basic. This is called as netlist. So here netlist, what you have only, this is called as a library name, library cell name or reference name. This is called as library cell name or reference name. This is called as instance name. This U1 is called as instance name or cell name. U1 is called as cell name. And this is called as port mapping, right? Port mapping means A1 pin of your AND gate is connected to which net. A2 pin of your AND gate is connected to which net. Output pin of your AND gate is connected to which net. So you have gates information and connection, right? You also have connection here. You can see N4 is output of, right? N4 is output of AND gate. N4 is output of AND gate and it is input for OR gate. This N4 net, you can see here. N4 net is output of AND gate and this same N4 net is input for OR gate. So my tool can understand that. My PD tool or synthesis tool can understand that, okay, I have connection between output of AND gate to input of OR gate. So this is called as netlist. This is called as netlist. This is called as netlist. So here also, right, you can see OR gate. Your N5, you can see N5 net is output of OR gate output pin, and N5 net is input to inverter input pin. So my tool can understand that there is a connection between OR gate to inverter. So this RTL netlist is also Verilog program or VHDL program. It has only gates information and connection between the gates. That's it. No behavioral description or no assigned statements. Right. So that is called as gate level netlist. What are steps in logical synthesis? So what are steps in logical synthesis? Can anyone tell me? So first step in logical synthesis is read the right, read the input files. Right, read the input files. See, sometimes HDC will not read at the beginning because HDC we have to write. We have to write the HDC. Even we can write the HTC from the beginning only, because any of set input delay, set output delay, right? Clock ports, set input delay is defined on input pins, input ports. Set output delay is defined on output ports. So we can write it beginning only, or we can do one cycle of logical synthesis, then we can write the HTC. So the steps in logical synthesis is, first read the input files, all the input files you read. What are the input files you have mentioned, right? For logic synthesis, you read it. In synopsis, when we read input files, right? For like a library file, we have target library, we have link library, all those input files we read. So next is, right, analyze the RTL. Means whether analyze the RTL means like verify whether RTL can be synthesized or not. Whether I have any constructs in the RTL which cannot be synthesized. So analyze the RTL. Probably it will be already, right, CDC check they will do, or linting they will do. Before synthesis, right, they will do linting, or CDC check they will do. In linting, they will check that whether all the constructs present in RTL can be synthesized or not. So analyze the RTL, whether we can synthesize
Sir, what is the name
RTL
of
or
the
hmm,
what is that name of the process you just said?
linting.
Okay, and that is for which tool does that?
So they see the different systems has different linting tools. Different companies will
Okay.
come with different linting tools.
Okay.
So like you have spyglass from Synopsys and Casper Gold from Cadence. So even you have few tools from Mentor Graphics also. So generally in our institute we use spyglass. From
And
Synopsys
sir,
we use spyglass.
like how would they know if is it possible after we provide RTL, I mean gate level netlist, and they start off with PD, and then there is an actual issue with whether the code can be synthesized or no. Can that be
See,
a
we are not
possibility?
doing. No, I didn't understand. Please repeat once again what you told.
Like for example, if you are running a PD flow,
Hmm. Hmm.
and you have a synthesized RTL and you're running the flow,
Synthesis
can they
netlist.
go?
Okay. Hmm.
Yes, and can they go back and check if again whatever netlist was synthesized, is it right or wrong? Can they find out in the PD flow?
See, the netlist they can verify. They cannot verify the RTL, right? Because already it is synthesized, right? If RTL cannot be synthesized, you cannot pass from this stage only. RTL stage only you cannot forward it. From synthesis stage only you cannot forward it. If RTL cannot be synthesized, your tool will never synthesize it, right? But
Okay,
if
you
there is
said
a problem, if there is a problem in netlist, like in a netlist we have multi-driven net,
okay,
right? Unconnected ports we have, unconnected pins we have. If any problem in the netlist, that can be verified. That can be verified in the synthesis stage also. We can verify the problem in the netlist can be verified even in the PD stage also. So we have check netlist. So check netlist will report all these things.
okay,
So, but in the PD we cannot verify. Right? In the PD we cannot verify this one. Right? RTL. RTL cannot be synthesized or not. We cannot verify because The reason is we have already got the netlist, right? If RTL was not able to synthesize, then we will not come out of synthesis stage only. The RTL will be in the synthesis stage only. But problems in the synthesized netlist, this synthesized netlist, problems in this can be verified even in synthesis stage, even it can be verified in PD stage. If there is a problem, right, then you have to obviously you have to communicate back to the synthesis team. Like the netlist is showing multi-driven nets. Multi-driven
Okay.
nets means one net is driven by from multiple drivers. Multiple cell is going to drive one net. Some net is driven by multiple drivers.
Hmm.
Then there is a confusion on this net, right? Which output I have to take? Whether I have to take output of this cell or this cell. This is called as multi-driven net.
Okay.
So you have some ports in the design which is not at all connected, left unconnected.
Hmm.
So if all these issues, so in the netlist you have assign keyword that you can solve in the PD stage only. In the netlist you have assign keywords. Assign keyword should not be there. In the netlist you should typing only this much cells and its connection. Only you should see this one. You should not be seeing any other things. Declaration is okay, like input, output, wire declaration is fine. You should be having only cells and its connections. You should not be seeing any assigned keywords. So if that is there, then even you can report in after synthesis, even that you can report even in PD also.
Okay. But in industry, they run like and all right. That like right to understand the logic.
See, after PD, after
Okay.
giving the floor plan def, right, we also
Hmm.
do synthesis once again. That is called as physical aware synthesis.
Yes. Huh.
Right? By using the same RTL, we do physical aware synthesis once again
Hmm.
after giving floor plan def.
Hmm.
So during that case, again, if the RTL has a problem, even we cannot synthesize at that point.
Okay.
That is, I am discussing now logical synthesis. I didn't come to that stage. Right? Even we will cover that. Physical aware
Oh.
synthesis. Physical aware synthesis, I'll cover that. Just I am in the
Oh.
logical synthesis now.
Okay.
So analyze the RTL, right? Whether we can synthesize RTL code or not. So probably that will be also done in a linting team before the synthesis. They will be doing that. So before the after the RTL team and before the synthesis team, we have two teams again, right? The linting team and CDC team, like clock domain crossing checks. They will insert some synchronizers. So both team will come into picture and they will both team will insert that. So linting team will check whether all the constructs in Verilog or VSTL can be synthesizable or not. If we cannot synthesize, then they have to modify it. For example, they have used some for loop which cannot be synthesized. Then you have to modify everything. So after analyzing the RTL, next is elaborate. Right. So in elaborate, resolve hierarchy in the RTL, resolve hierarchy in RTL. Because RTL can be like hierarchical way, right? You will be having top module. So this top module will be having right different sub modules. For every module calling, right, you should see that there is a module definition or not. For every module calling, if you have to find whether there is a module definition or not. If module definition is not there, then hierarchy is resolve hierarchy becomes very difficult. For example, I have a top module, right? I have a top module here. Like I'm writing the top module. Here I'm calling ALU block. I'm calling ALU block. For this ALU block, right, there should be a separate program. Module definition should be there. Separate program should be written for ALU block. I have SDRAM block. I am calling SDRAM block in the top module, and separate program should be there for SDRAM block. There should be separate program for SDRAM block. So I am calling SDRAM block from the top module, but the program, separate program for SDRAM block is not there. You don't have separate program for SDRAM. So you are doing module calling, but the module definition is missing for this. Then the resolving the hierarchy fails. So elaboration will resolve the hierarchies and it will convert design into GTECH cells, and it will convert design into GTECH cells. After elaborate only, my RTL will convert into gate level and its connections. But in this, I don't have cells belonging to this library file. What are the cells present in library file, right? That will not be present in the result of elaborate. After elaborate only, my design will convert my RTL into gate level. But here I will be having GTECH cells. So GTECH cells are picked from GTECH library. There's a library called as GTECH library. Every synthesis tool will be having this GTECH library. It has generic cells. It has generic cells. The GTECH library has generic cells, not mapped to any technology. Not mapped to any technology. Means the what is the meaning of this? Whether all the concepts present in RTL I can map to any one particular cell or not. That is what we are trying here. So initially my design will be mapped to GTECH cells. So after this elaborate also I can write out the netlist. So I will be seeing the design in the design I will be having only GTECH cells. So GTECH cells are picked from GTECH library, and this GTECH library will come along with synthesis tool. Every synthesis tool will be having this GTECH library. So it has a generic cells and not mapped to any technology. You have generic cells not mapped to any technology. Then last step is mapping and optimization. Mapping and optimization. Now what happens is I have, after elaborate, I have cells, right? I have the cells in the netlist belonging to GTECH library. It is independent of technology. Mapping means map the cells to the cells present in .lib. And optimize the design to meet the timing, right? To meet my clock frequency, whatever the clock frequency I defined here, to meet the setup time, right? Optimize the design. Optimize the design to meet a setup time and to reduce the power consumption. And according to UPF, if you want to insert any level shifters, multi-voltage design requires level shifters, so tool will add level shifters. So if you are using power getting design, tool will add retention cells and isolation cells. So power switches will be added only during PD time, not be added now for power getting design if you have. So after this mapping and optimization means map the design to, right, now the design to the cells present in library file. The library file is dependent on technology. Library file, that is .lib, and optimized design, and optimized design, and optimize the design to meet timing and power, and to reduce power. These are the steps present in logical synthesis. After mapping and optimization, right, you will get the final netlist. So in the netlist, after mapping and optimization, the mapping is done, right? Mapping design to cells present in the library file. So after mapping and optimization step, my my netlist will be having the cells present in the library file, this library file. That is what the thing, right, we'll be having. So after this, right, we have to do checks, different checks we have to do. Checks after synthesis. This quality of netlist, which netlist should not have any information apart from this cells and its connections. It can be a hierarchical design, means you will be having a top module, next you will be having a sub modules, sub modules may having some other sub modules, that is okay. But you should not be having anything apart from that. You should be not having anything like you should be having only cells and macros and port mapping. That's it. You should not be having any assigned keyword or any behavioral description in the netlist. You should not be having any unconnected nets, unconnected ports, unconnected pins, multi-driven nets. Right? So all these things should not be present in the netlist. So first we will verify the quality of the netlist. So next is, right, we can verify the timing. So setup timing check we can do. So next is, see, hold is not required actually, because after synthesis we'll not do hold check, we'll do only after CTS. But just we can check whether hold is on what margin the hold is violating or hold is met or not. If hold is violating by huge margin, what is the reason? We can just verify about that. Because actual hold check is done only after CTS, because hold depends upon skew. Actual skew is produced only after CTS. During synthesis until CTS stage of physical design, clock is ideal. So we'll not do hold check. And we can do DRV check, like max cap and max transition check. We can do max cap and max transition check. Next, we can analyze the power. Analyze power. So again, power, if we take, right, we will analyze how much is your leakage power. So to meet the timing, if my tool has used all the LVT cells, then leakage power is more likely to shoot out. All right. So next is your switching power or internal power. So internal power is nothing but the power dissipated, right, inside the standard cell. So due to charging and charging of the internal capacitance, charging and discharging of internal capacitance, and short circuit current. If I have a inverter, right, or if you take an AND gate, you take a AND gate. So AND gate has what? First you have a NAND gate here. So its output of NAND gate will connect to inverter. This inverter is the NAND gate. So these are the inputs for AND gate and is the output of AND gate. Y output and A1 and A2. So this AND gate has like output capacitance, right? So charging and discharging of this output capacitance is called as switching power. But you also have internal capacitance here. Right? You also have internal capacitance here. After AND gate, this is your AND gate, this is your NAND gate, this is your inverter. After NAND gate, you have inverter, you have internal capacitance. The charging and discharging of this internal capacitance, along with short circuit current, means direct for a moment, direct current flows from VDD to ground. That's called short circuit current. So both the currents, the power dissipated within the boundary of cell, that is called as internal power, and power dissipated due to charging and discharging of the load capacitance, that is called as switching power. To analyze the power consumption. So this is about your logical synthesis. So in the logical synthesis, right, what we have to do is we have to write this STC file. We have to write the UPF for multi-voltage design, right? We'll write the UPF. So we'll understand how to write the UPF. We'll understand how to write the STC file for logical synthesis. Then we perform logical synthesis and we will analyze all these results. But to write this UPF, right? To write this UPF, first you have to understand the STA. STA is very, very important. Static timing analysis. You have to understand what is STA. So if you understand STA, then only I can understand what is setup timing check. Correct? So if I understand that STA, then only I can understand why all these things are required. So set input delay, mainly it is used to handle into rest path. Set output delay, mainly it is used to handle rest to out path. So we have to understand static timing analysis. In static timing analysis, right, we understand what is cell delay, and it depends on what parameters. Then we understand cells with, cells with different drive strength, and different VT flavors. So what's the difference? Right? So if I have different drive strength cells and different VT flavors, what is that? How does it affect your cell delay? That is what we are going to discuss in STA. So next we discuss about different types of clocks. Different types of clocks. Like we have different types of clocks like master clock. How to define it? A master clock. Right? How to define generated clock? How to define virtual clock? You understand that? So why virtual clock and how to define virtual clock? Next we'll understand different types of path in different types of timing path like rest to rest path, into rest path, what is out to rest path. Then you'll understand what is Q. So how do we define Q, right? How do we define right latency? What do we mean by jitter? And what is uncertainty? Clock uncertainty. We understand this. Then we'll understand what is a setup analysis and hold analysis. Setup and hold, including skew, jitter, and uncertainty, including a skew, and uncertainty. Then we will discuss about how to handle into rest path, and rest to out path. So how to handle into rest path, how to handle rest to out path. So to handle into rest path and rest to out path, right? We have to define set input delay, set output delay. So we have to define set driving cell, set load. Then we'll discuss about modes. What is modes? Corners and scenarios. So after that we will also discuss about derate, on delay, types of derate, how to apply derate, how to define derate. That is it.
So rich to rich part.
Yes, here only we are discussing setup and hold. Here we are discussing with rest to rich path only.
Okay.
So next, how to handle derate on the delay, derate on delay, how to apply derate on delay. So next we'll discuss how to handle asynchronous, handle asynchronous inputs, and clock domain crossing. If you have clock domain crossing, how to handle. Next we'll discuss about what is a recovery and removal check. This is mainly done on asynchronous reset. recovery and recovery and removal checks. Then we'll discuss about STA at different stages. See how we do STA at different stages. See, when I am using logical synthesis, after logical synthesis, what is STA? Right? After placement stage, what is STA? After routing stage, what is STA? How to do STA? After CTS stage, what is STA? During logical synthesis, we will get net delay from wire load model. And clock is ideal. After placement, we'll get wire load model from TLU plus file. But clock is ideal. After CTS stage, clock is propagated, but still we use a TLU plus file. After routing, clock is propagated, we can extract the SPEF by using star RC. That is called as how to handle ST at different stages. That we will discuss. Next is low power technologies. Low power technologies. Like what do you mean by power getting design? What do you mean by multi-voltage design? Low power technologies means like what is multi-voltage design and what are the new cells come into picture if I use this design? What is power getting design? What is clock getting design? So these are all the different topics what we cover in STA, static timing analysis. So when I cover all these topics, right, then you'll understand how to write this STC. So first what I do is I will start with STA. So we'll cover all these topics. Then we'll start with synthesis. During synthesis, we'll write STA, SDC, and we'll write UPF file. Then we'll synthesize one logic. Then we'll perform logical synthesis. After logical synthesis, we'll do all these checks. So next you have one more type of synthesis. Next you have one more type of called as physical aware synthesis. See, we'll take a 15 minutes break. Now time is 3:25. We'll continue at so 15 minutes break you take. So it start at 3:40 again. Right? We'll continue at 3:40 again. Yes, we'll continue again. Yes, online it's audible.
Yes, sir. Yes.
Yes, sir. So, right. So one more type of synthesis is physical aware synthesis. Right? So physical aware synthesis, the difference between logical synthesis and physical aware synthesis is right. For physical aware synthesis, physical aware synthesis, no floor plan information. Right? In the PD, we have floor plan. Physical aware synthesis knows floor plan information. So we'll give the floor plan information of PD. So that we will feed back to this synthesis tool that is called as physical aware synthesis. So this logical netlist, right? This logical netlist, what is the flow is, right? This logical netlist, this whatever the netlist we get after logical synthesis, that is called as a logical netlist, is given to PD, right? Physical designer. So physical design team will create core area, right? Die area, will create core area. They'll create port placement, and create macro placement, create macro placement, create core area, create port placement, create macro placement, and wherever you want apply the blockages, apply placement blockage. Placement blockage means the area which is restricting the placement of cells. Apply placement blockage in PD. Then create def. After this, create def. After this, create def. Def stands for design exchange format. And this def file, right, you give input for physical aware synthesis. So what is the thing is, right, after getting the netlist, what you are doing is you will create core area, right? You will create die area, like this, create core area and die area. After creating core area and die area, create the port placement. If it is a full chip level design, create IO part placement, right? Create port placement. Create port placement. After port placement, place the macros. Macros are complex cells, right? Place the macros wherever you want. So after placing macros, right? Apply the, see, I only place the macros, not standard cells. After placing macros, right? Apply the blockages in the macro channel like this, right? Placement blockage you apply in the macro channel. This placement blockage, right? This is placement blockage. This is placement blockage, right? Apply wherever you want, you apply placement blockage, like partial blockage or soft blockage. Any blockage you want, you apply it in the macro channel. If it is a multi-voltage design, then create the voltage area also. Right? Create the voltage area. If it's a multi-voltage design, create voltage area. So this floor plan, right? You create a def, right? This floor plan you create a def, and this def, right? You forward to physical aware synthesis tool, right? This you convert to def, like design exchange format. Right? Then you give to physical aware synthesis tool. Now the physical aware synthesis will do the physical synthesis to meet this area, right? Will do synthesis to meet this area. So it will normally, right, the RTL, whatever the RTL it has, it will normally do the logical synthesis and will try to place the cells in each and every area. Right? It will try to place the cells in each and every area. Right? If it is after placing the cells, it will verify the congestion. Right? Means congestion means whether all the cells can be routed or not. It will verify the congestion. It will verify the timing. So if congestion and timing is not good, it will resynthesis. It will do again. It will do the optimization. Again, it will do the optimization on the RTL code. It will do logical reordering or logical reconstruction, logical restructuring. It will do so that all the standard cells are placed in this core area without congestion and without the more timing violation. Right? Now this
Sir, I
tool
have a
knows
doubt.
where to place the cells. So it will do the coarse placement, right? Rough placement it will do during synthesis only. It will do the rough placement.
Sir, I have a doubt.
Yes, tell me.
So when we do physical aware synthesis, you said it will check, it'll place these macros and all, and then do it, right?
We
Here,
are physical awareness will not place the macros. Physical design engineer will place the macros.
yes, yes, but that floor plan will be provided again for physical aware.
Yes, this floor plan, this standard cells are not placed. Standard cells are placed means this rough placement will be done by physical tool, synthesis tool, physical aware synthesis tool. But only the macro place design, right? This macro place design and port place design will be given to physical aware synthesis tool.
Yes, so will it also have some end caps, tap cells, including those it will consider, or only without those?
Yes, yes, you can also apply that and you can forward because those are all the blockages, right? Those regions you cannot place. You can even place those cells and then you can forward. If you don't have end cap and tap cells in the library, you can apply blockage at that point and then you can forward. If you have, you can place those cells and then you can forward. Even you can add end cap cells and tap cells. Then you can add and then you can forward. Because in that regions, standard cells should not be placed. So you should add that and then you should forward.
Okay, okay.
Right. So here I'll also mention right, apply placement blockage. Right. I'll also mention add add end cap and tap cells. Right? Then create def file, and this def file is forwarded to physical aware synthesis. Then what are all the inputs for physical aware synthesis? Inputs for physical aware synthesis. What are the inputs? So the same inputs should be present, right? The same inputs are required. These are the inputs. These inputs. The same inputs is required even for physical aware synthesis. This HTC, right, explanation will remove. Along with this, right, we want technology left. Technology left or technology file. In Synopsys, we call it as technology file, or in Cadence, we call it technology left. So, technology file is important. Technology file or technology left. So, we have site rows information there only, right? Site row information. And what is the pitch of a metal layer? So, all those information is present in technology left only. Based on that only, your tool is going to calculate the congestion and cells are placed. So, technology file is important. Next is physical information of cell is important. Physical information means LEF. Right? Layout exchange format is important. Layout exchange format required. For each and every cell, I should be knowing what is the width and height. So width and height is present only in LEF. And what are the layers in between? Inside those left, right? So layout exchange format LEF is important. So LEF in Synopsys we use Milky Way format. So next is floor plan depth is important because floor plan depth only tells where we should not place the cells, right? Floor plan depth is important. So what is the floor plan depth? Right, we already mentioned here. In PD, we should do all these things. This floor plan depth, you give us one more input. Then, what is important is very important step is right. Very important file is PLU plus file. See, when my tool does the course placement, right? After this during physical aware synthesis, when my tool does the course placement, so I can estimate what is the net length. Net length cannot be estimated. Net length can be estimated. I can estimate what is the net length like this. By using global routing, I can estimate what is the net length. When I know what is the net length, because I already know what is the location, cell location I already know. After knowing cell location, I can estimate what is the net length. After estimating what is the net length, alright, I can easily find this net resistance and capacitance value by using TLU plus 5. TLU plus 5 is used to obtain RC values of a net. Values of a net. When we know cell location, during logical synthesis, we don't know what is cell location, right? So we didn't use the TLU plus file, but we used this one. In library file only, we have wire load model. My tool is going to calculate this RC values by using wire load model. But here, to calculate net delay, right, we use TLU plus file. So during logical synthesis, right, during logic synthesis, we use wire load model. Wire load model in in lib file. During logic synthesis, we use wire load model in .lib file. So these are all the, so if you have like scan def, even you can also provide scan def information. Scan def also we can give. Scan def file we can give. So these are all the inputs for physical aware synthesis. So what is output of physical aware synthesis? Right. Output of physical aware synthesis. So I can use the netlist. See here synthesis is done by physical aware. So my synthesis tool knows how many area is left out for me for placement of cells. If I want to do any logical restructuring to meet this area, I can do. And it can do how to meet the, so with this floor plan, how to meet the timing. What cells have to upsize, what cells have to do VT swapping. Any logical restructuring I should do from RTL, I can do it to meet this timing and to reduce the power.
Sir, what will be the uh, so after the floor plan is provided,
Mm.
after floor plan and whatever we have added, there will be some amount of cells we'll be adding after place up, clock up, route up,
No, those are
ECOs.
extra cells. Yes, yes.
Yes,
Those are
so
extra
it
cells.
will be leaving so much space regarding on the floor plan itself, right?
See, while creating this core area and die area only, we would have used utilization.
Yes, yeah.
With utilization only we would have done. So that those cells, by keeping in that in mind, right? For example, 5% of cells can be added in place of stage, 5% of cells can be added in CTS stage, and 5% of cells can be added in routing stage. So
Hmm.
15% extra space you keep, and then you proceed with the design, right? That you already taken care.
Okay, okay. Hmm.
That you have to
So
take care while
we,
building. See, I cannot see, for example, for total standard cells and macros. If I want
hmm,
100 micrometer square area, for example, some 1000 micrometer square area, I cannot create
hmm.
my core area only for 1000 micrometer. I should
Correct,
also
yes.
consider some 20% extra, 30% extra, 25%
Hmm.
extra. So in the block level design depends upon the chip top, how much extra area is giving.
Hmm.
So they would have already considered that extra area. Without extra area only, you should do the physical design, or else you cannot complete. You will end up with overutilization and many shots.
Yes, so that will be considered in the synth stage also, no? If when waiting floor
No, no, it will
plan.
have to be considered. Yes, that is the extra area is already present in this.
Okay, okay. Hmm.
Extra area is already present in this floor plan def. See, only see after going to the physical design, we cannot do logical restructuring. Means logical restructuring means changing of cells. I cannot do.
Correct, yes.
Only I can fix the violations by VT swapping or by upsizing the cells or by increasing the skew, decreasing the skew. Right? These methods I can do, but I cannot do logical restructuring. Logical
Correct.
restructuring can be done only by synthesis tool. So
Hmm.
we will take this floor plan, we will go back to synthesis and we'll see whether logical restructuring can be done to for this floor plan. We'll check that.
Okay, okay.
That is called as a physical aware synthesis. That's it, right?
Hmm.
Even my synthesis tool is fixing by using VT swapping or upsizing the cell few violations. Even that I can do during physical design also. But only
Correct.
reason for going physical aware synthesis this with this floor plan. So you gave me the net list with zero interconnect delay, right? Or net delay obtained from wire load mode. It's not actual thing, right? It's not the correct thing. What are the logical restructuring you did? Everything, whatever
Hmm.
you did, that is for wire load model. That is not the actual delay. Now TLU plus is having almost nearest delay to the actual delay. Even TLU
Hmm.
plus is
Hmm.
also not a TLU plus file, right? It is using global routing information, right? And you know the net length. By net length, you are going to get RC values. So that is almost nearer to your net delay, total net delay. Now with this net delay, what are timing violations you are getting? If you want to do any logical restructuring, you do it. One more time, you do it.
Oh,
That is what the agenda behind the physical aware synthesis. So after this, if you take this netlist means that will almost correlate with your physical design, or it will not correlate. So after doing logical synthesis, I will be getting almost negligible violations. But immediately when I go to physical design, I will be seeing more than 1000 or 1500 violations with the netlist
correct. Yes, yes.
because of the right, both are not matching. Right here, I used a wire load model. It is
Hmm.
calculating the delay based on the fan out. But in the real chip, net delay is calculated based on the net length.
Hmm.
Both are
Hmm.
totally different. So what we do is okay, we will give the real information. Then if you want to do any logical restructuring, you do it. So for that reason, we use physical aware synthesis.
Oh, okay. Hmm.
So output of physical synthesis is netlist, right? Where cells are where cells can be modified. The cells are different from logical synthesis. It can be present different from logical synthesis. Second thing is you can also get the def file, right? From physical synthesis, you can also get the def file where course placement is done. Where course placement is done. So even after this, I can get the congestion report. I can get congestion report. Timing report and power report. So in this course, we'll also do this physical aware synthesis. Right? This also we'll do. These are all the outputs of physical aware synthesis. So the main course, right, will start from STA. Right, we'll see different things in STA, right? Each and everything in STA. Including few labs also in between. Setup means setup and hold. How is the setup and hold report? So how to define modes, corners, and scenarios for any design? How do we apply derate? What's the commands for that? Right? What is recovery and removal check? Right? We'll see the real timing report. How the recovery and removal check is done. So
Even
STA
how
at
to
different stages. Yes, tell me.
false path and all will help us check, sir. False path. Uh,
Yes, sir. So there is timing exceptions. Even that is a false path and multi-cycle path. Even this we'll see how to define a false path. And by default, some paths are false path because if I have clock domain crossing, by default, some paths are false path. So this flip flop is driven from one's clock. right? Clock 1, right? This flip-flop is driven, this flip-flop is taking clock 2, and these two clocks, clock 1 and clock 2 are asynchronous to each other, but you have a combo cell connecting between these two things. But clock 1 and clock 2 are asynchronous to each other. So automatically this path will become false path because STA cannot be done on asynchronous clocks. Right? We cannot do STA on asynchronous clocks.
Okay. Yes.
So by default, few paths are false paths. Alright. So we analyze that in the real design why few paths are false path, and in the real design, right, what is the results of check timing. Check timing. So extract spef from the router DB. Even this is not our area of interest. We'll also do this. Extract spef from router DB, router database, router design. Right. Do sign off using prime time. Doing sign off using prime time. Using prime time. These things we'll do, right, in STA. So after STA, we'll start with logical synthesis. In logical synthesis, right, we perform analysis of, here we'll perform analysis of RTL, why it cannot be synthesized, few constructs. Then we'll write this STC file for different modes and different scenarios. Then we'll, for a multi-voltage design, right, we'll write the UPF. We'll understand how to write the UPF. So after writing STC and UPF, right, load to the tool and perform logical synthesis. Then understand the quality of the results, like quality of netlist, setup, check, max cap and max transition violation. Analyze the power, how understand how power can be reduced. Then after logical synthesis, again we can do sign off, timing sign off by using prime time. We are using timing sign off. We can use timing sign off can be done by using prime time. So only thing here is after routing we use spef file. Here spef file cannot be used because it is synthesis design. So tool will use RC values from wire load model only. Prime time will use RC models from wire load model only. Or SDF can be used. Standard delay format can be used. So after logical synthesis, then by using ICC2, we create core area, right? Die area, port placement, macro placement. We will use add end caps and decapsules. What is a def we are getting, right? A def we will take and we will load all these files and we'll perform physical aware synthesis, and output of physical aware synthesis we are going to verify. Right? So this is what we are going to do in this design, right? Or in this project, this course. So in this course, first we'll start with STA, static timing analysis. So understand STA based on real-time project. Even it is PD also, right? Real-time project. Next, extract stuff and timing sign off. Do timing sign off using prime time. For multi-voltage design. Next is, so this requires almost 6 weeks, almost 5 to 6 weeks it what only on weekend. Next is logical synthesis. We'll do logical synthesis. So in logical synthesis, we will write SDC. We will write UPF. We'll learn how to write SDC UPF. We will do logical synthesis in DC compiler. Sign off we will do, right? Sign off we will do in prime time.
Genus and
After this,
DCR.
yes, genus and DC are same. Genus is used in cadence. DC we will use in synopsis. So prime time we use here. I think they will use tempus. In cadence they will use tempus. Then we will use physical. We'll do physical aware synthesis. Before physical aware synthesis, we will do all the steps in IGC2. We'll do floor plan in IGC2. Perform floor plan in IGC2. In IGC2. Then perform physical aware synthesis in DC shell in topographical mode. Physical aware synthesis we should do in topographical mode. Perform physical synthesis in topographical mode. So this is what we'll do. Course. So this requires 6 weeks, correct? This requires almost 3 weekends. 6 weeks means it is like I can tell only on weekends I'm telling, like 12 classes.
That will include lab also, no, sir? STA?
Yes, lab also.
Okay.
See, that is what extract spef. Timing sign off we will do using multi voltage design. This spef can be extracted only on the router DB of physical design.
Mm-hmm. Yes.
That is what. So that is done only on the router DB or the physical design. Right. So this requires almost some 7 classes. This requires like 4 classes. This requires like 3 classes. So only 13 to 14 classes are required. So in one class, 3 hours will do. So 14 classes we want Totally for each class we will do for 3 hours. Yes, any doubts you have, you can ask me now. See here you can also learn a small amount of TCL. So even TCL is taught using small amount of TCL is also taught using DC compiler. So any doubts you have, you can ask me. This is the course content. So sessions will be on only on weekends like Saturday and Sunday for 3 hours. Okay, thank you then.